example, we have to scale it and play with it. On the other hand, with cosmological simulation, you are God, you know everything, you know how galaxies evolve, you know how galaxies merge, so you can extract more information on the host galaxies of the systems that is not as easy to get from data-driven approach. So you can get complementary results from this complementary approach, and then if you get something that is not that different from each other, you are more happy than if you follow just one approach. Of course, if somebody comes here and tells me I measured the metallicity evolution of the universe with the greatest accuracy ever, I'm happy and I go just for the data-driven. I'm over time, so I think I will skip the information about the galaxies, the host galaxies, but you can ask me if you're interested. This work done basically by Celeste Artali in Innsbruck, so just ask her if you don't want to ask me. And I just would like to thank my wonderful group, PhD student and postdoctoral fellows. Most of the work I presented here would not have been possible without them. And here are my conclusions, and I thank you for your attention.
Questions? Yeah, Dan.
Yeah, can we go back to the cosmology, the rate versus redshift?
Yeah.
I'm just curious, there's obviously striking drop-off once you don't have any star formation at a far high enough redshift, but how robust is the redshift of that drop-off? Will we learn anything by observing where that happens?
Well, of course, it's limited by the resolution of the elastance here. Furthermore, what I'm more worried about is that Elastris as well as Eagle and all the other, most of the other cosmological simulation has no prescriptions for population 3 stars. So this is something you may want to put by hand. Anyway, this is not so dramatic because even if population 3 stars are tremendously effective in producing binary black holes, they shouldn't produce a significant fraction of what we are seeing here. There are many papers doing that. I can quote Harvig and collaborators, and they say probably up to 1% of the GW 150914, so up to 1% of the most massive objects.
So when you were discussing this, the dynamical scenario, you found a population of black holes in the pair instability gap, above 60 solar masses. And then you said it is not because of second generation, something else. So I would like to understand what that something else is.
Yeah, let me show a cartoon that makes it a little bit clearer. So what happens is that these objects come from at least one merger between two very massive stars, usually more than one. And one of the two stars has already developed a helium core or a carbon-oxygen core, and it merges with a massive main sequence star. If we assume that the merger does not lose too much mass of the hydrogen envelope, then we get something with an oversized hydrogen envelope with respect to the helium core. Then things are dominated more or less by the time scale for burning helium into something else and carbon oxygen into something else, not by the time scale for converting this hydrogen into helium, which is much longer. And then this, under very special condition, this merger remnant can collapse to a black hole when the hydrogen envelope is very oversized and the helium core is below 30 solar masses. So if you assume that the hydrogen envelope efficiently collapses down to a black hole, you can produce this. And then,
so you're assuming that all of it falls into the black hole.
Yeah, this is always the only way you can do. But it's nice because if in the end this is something that is not observed, then you are happy because your stellar evolution is not that complex.
But has anybody actually done a supernova
Calculation with that?
evolution with one of these objects?
No, that would be super interesting.
That would be
Actually,
really
we are thinking of it. Before this, I would start with 3D hydrodynamics of this kind of mergers, because if you browse in the literature, you find people who say 90% of the mass is lost, and you find people saying up to 20% of the mass is lost. So Yeah,
think
and then
Andrea Antoni, who's a graduate student at Berkeley, is looking at, with Elliott Quadrant, is looking at some of the early infall, not the whole thing.
Oh, great.
But it's like, do the convective plumes form a disk or not? Maybe that matters for the feedback of the subsequent infall. So it's not the whole story, but it's a tiny piece of it.
Meanwhile, Virgo are going to show us some of these objects.
Yeah, probably they come in before the theory.
They will probably come before.
Yes.
So your models must produce predictions for things like the spin of the black holes and things like that. And observation of black holes will put strong constraints on this. It's observation of gravitational waves.
Or spins.
On the spins.
Well,
so there must be specific things which, predictions from your model for that.
Well, actually, I don't like spins, and the reason is that
I don't like it, but
if things are already as uncertain as you have seen in my talk about mass, and we think we understand mass quite well, they are terribly uncertain about spins. So,
angular momentum exists, we know, and the spins might be aligned. These are some generic things.
Well, there is one thing you can know better. There is one thing you can know better, that is...
Sorry, go ahead.
No, please go ahead.
You interfered, I didn't.
So my personal view on this is that, okay, we kind of get the orientation quite well, in the sense that we know dynamics is going to lead to isotropic distribution, at least for exchange black holes, while stellar evolution, binary evolution tends to align things unless a supernova does something funny. But what is really hard to be predictive about is the magnitude. Because if I take just all the angular momentum that is inside the portion of the star that is going to collapse, usually you get very large values of the spin. But this is like really a strong upper limit of what you expect, because even neutrinos, even if you don't produce anything like disks, things like that, even neutrinos can carry away some of this. So at some point, now we are doing spins with toy models, especially because of the orientation. But for the magnitude, I prefer not to say I'm predictive. I prefer to play with masses and merge rates, which I think is already a lot of information.
Thanks.
Well,
I think we have time for one more question. Carl.
I actually wanted to ask about the eccentricities that you get from the low mass clusters. My understanding is that most of the time you'll get higher eccentricities because they'll be thermalized, which won't necessarily give any of the ridiculously high gravitational wave captures. Or at least not at the kind of rates that you get from like globulars and neutron star clusters.
so this is about eccentricity, about rate. About eccentricity, no, we actually get quite low eccentricities. I stupidly don't have the plot here, but I can show it to you. Is in the paper, the first paper by Hugo. We get eccentricity that are significantly higher than the isolated binary case, but not that high. So, for example, we don't have the 0.8, 0.9 eccentricity of the black holes by capture that you have, for example. And the reason is twofold. One is that here, anyway, very hyperbolic capture are quite unlikely, and the second one is that anyway, we don't have the high post-Newtonian terms, so I think this is one of the things that we don't model really well. As to the merger rates, here I have just the merger efficiency, not the merger rate, but I think we'll do. Because we are still crunching the merger rate. So the point here is the following. With globular clusters, you tend to have merger rates like up to 20 events per gigaparsec cube per year that will work for you. And this is reasonable because, it's more than reasonable, it's okay. Because most globular clusters formed many gigayears ago. So what we are, and then they stop forming for some reason. So what we are observing now is basically the tail of the merger burst that happens several gigayears ago. In contrast, youngster clusters are more difficult to model because they are less massive. Dynamics is less intense in youngster clusters than it is in globular clusters, but they form all the way down from high redshift to nowadays. So it depends on actually how much of the massive stars, what is the fraction of massive stars that form in these youngster clusters. And if you look at the merger efficiency, these stars here are the merger efficiency that we get from youngster clusters. The lines are the merger efficiency from isolated binaries. And you see that they basically don't enhance much merger efficiency. They don't enhance it definitely at low metallicity, but they enhance it at high metallicity. So it depends actually on what fraction of stars form in star clusters or in the field at which redshift. And this is something we want to do with the Bayesian analysis to quantify it. So in principle, they can be responsible for most of LIGO-Virgo binary black holes, but I will answer your question in 1 year or so from now, I hope.
Excellent. Let's thank our speaker one more time.
That's even before you put binaries.
So Ramesh, how would you do? I've wondered for a while how you would do the simulation of a red giant envelope collapsing. Because you have to excise the core if you want to do the envelope.
You can't do the full product because the time scale is so different.